Alright, in this video we're going to explore what happens when you take derivatives of certain kinds of power functions. We've learned how to take derivatives using this concept called first principles, where we set up an average rate of change and we apply a limit to turn it into an instantaneous rate of change, and that's how we found derivative functions. I'm sure you've experienced by now that it can be a painful process with lots and lots of algebra. However, after taking enough derivatives, you may start to notice a pattern. That pattern can be found through this matching activity that I asked you guys to do. And once all of these functions are matched with their derivatives, we could start to observe this pattern. So allow me to demonstrate. First of all, looking at function d, graph 4, and function 2, this is the derivative of that function. And I look at the 3 times 4 equals 12, and I see that the fourth power became a third power. If I wanted to generalize this step in between, how the derivative came about, it seems like I can shortcut the process. Instead of using my first principles, I can use this thing called a power rule. Apparently it seems to work out if I do the following. Take the 3, that's the coefficient, times 4, the original exponent, and then reduce the exponent by 1. Apparently the derivative has the effect of reducing the power by 1. So that happens, I get 3 times 4 is 12, and I get x to the third power, which is 1 less. See it again here with this particular power function. The coefficient is negative 1/4, the power is 3, so we multiply the power by the coefficient and get negative 3/4, and we subtract 1 from the exponent, and there we have the derivative. Now naturally the question would be, why didn't you tell us this in the first place? And the answer to that question is, how would we appreciate a shortcut if we didn't walk the long way once or twice? Moreover, the first principles, or the long method, helps us understand where derivatives came from and why they do what they do. But afterwards, now we can kind of circumvent that process by observing the patterns that emerge here. So how does it work in the context of differentiating a function such as this one? The first thing that we need to do is we need to make sure that the function is expressed in power form. So in other words, the square root of x is actually x to the 1/2, and a 3 over x can be expressed as 3x to the negative 1. And just as a reminder, x to the negative 1 equals 1 over x. I would ask you, why is that? Also, what I'm going to do is I'm going to take a constant value and multiply it by x to the 0 power. X to the 0 power equals 1. Why is that? Nonetheless, if we memorize it without understanding it, it doesn't change the fact that 12 times x to the 0 is equivalent to 12. We're just putting x with a power, so we can apply the same power rule to every term in the expression. So the power rule says, multiply the coefficient by the power and drop the power by 1. So here it's 2 times the exponent, and then the exponent subtract 1. Here's 3 times the exponent, and then the exponent subtract 1. 12 times the exponent 0, which is 0. Times the exponent, or x to the exponent minus 1. Clean it all up now. We can subtract the exponents here to get negative 1/2. We can subtract the exponents here to get negative 2. And we multiply 0 times everything and we get 0. Last but not least, we were given the problem in radical form with no negative exponents, so we're going to take our derivative now and convert back to radical form and no negative exponents. So this is the reciprocal of x to the negative 1/2, which is 1 over the square root of x, and this is 3 over x squared, and that is my new derivative function. Try to imagine if you use our first principles argument to differentiate this function. You might find it a little painful as much as I do just imagining it. Another example, in this case, once again, we need to take the function and convert it into power form. The biggest challenge here, of course, is recognizing the square root of x is really x to the negative 1/2, and, 1 over the square root of x. So here's 1 over the square root of x, which is really 1 over x to the 1/2, which is really x to the negative 1/2. To slice it another way, 1 over x to the 1/2 is equal to x to the 0, which is 1 over x to the 1/2. The law said we subtract our exponents, so I will, and then we end up with x to the negative 1/2, so no matter how you slice it. I've got to stop here for a second here, hold on. So, right over here, I've got 5x to the 1, that's easy peasy, and here we have x times x to the negative 1/2, so this square root of x I converted over, and then when we when we multiply these two together, we add the exponents, and 1 plus negative 1/2 is equal to 1/2. Or you can look at it this way: x to the 1 times x to the negative 1/2 is equal to x to the 1 plus a negative 1/2. Or you could look at it as x to the 1 over x to the half is equal to x to the 1 minus 1/2, which is x to the 1/2 power. So a couple different ways to get there, but nonetheless, this has to be converted into just one singular power of x, which I've done. And we put 4/5 x to the negative 2. Now we apply the power rule. Multiply the coefficient by the exponent, drop the exponent by 1, coefficient times the exponent, drop the exponent by 1, coefficient times the exponent, drop the exponent by 1. Now you can see I'm showing every single step in the process, even though I can do all of this work in my head. The problem is, of course, that fractions and negatives and all sorts of those other problems that emerge when we make mistakes doing mathematics will emerge if we do all of this work mentally. So at least for this chapter, if you want the highest level of success here, we're going to take our function and put it in power form. And before I actually write down the derivative using my shortcuts, I'm just going to show the middle step, and that is the multiplying of the coefficients and the dropping of the powers by 1. That's the derivative in shorthand. The power rule is what that's called. Then we do take care of all the arithmetic, and we convert back to the form the function was given to us in. So this then turns out to be the derivative. One or two more examples left. Here we might have a mistaken idea that in this function we can take the derivative of 2x minus 1 over the derivative of x. We'll explore this later, but it turns out you can't do that. When you have a quotient, you can't just take the derivative of the numerator and the denominator separately. So we have to do a little bit of cosmetics here to get this into power form. All we have to do in this case is distribute the x. It's 2x divided by x minus 1 divided by x. And so when we do that, oh, and by the way, this is just reminding us that you can't divide by 0. When I do that, I get 2x over x minus 1 over x, which in power form becomes 2x to the 0 minus 1x to the negative 1, which is, well, we multiply the coefficient by the power, drop the power by 1, coefficient times the power, drop the power by 1, and we get 0 plus x to the negative 2, or just 1 over x squared. So the derivative of this function is 1 over x squared. And finally, again, this function is a product. It turns out you can't take the derivative of the square root of x and multiply by the derivative of x plus 2 and that be the derivative. So since I can't, right now, I can't differentiate a product of two different functions, I again am going to have to convert this into a power function or a sum of power functions, and all I do is distribute the square root of x in power form. So here's the square root of x times x, the square root of x times 2. And then add the exponents, so that's 3/2 times 2x to the 1/2. Now the function is set up to differentiate with shortcuts, so I find f prime of x, 3/2 x to the 3/2 drop the power, 2 times 1/2 x to the 1/2 drop the power, and that's our final result. Clean it up to look cosmetically beautiful, and there you have it then. So the derivative of this function is this function. Maybe someday we can learn a shortcut that will enable us to find the derivative of a product or a quotient, but right now we're going to have to cosmetically redesign the function so that it can use our shortcut, the only shortcut we have, called the power rule. Let us not forget, this particular video focused on just the algorithm for taking the derivative using the power rule shortcut. That doesn't change the fact that we need to utilize our technology to make sure that our calculations are valid, and even here with the shortcut we could still make mistakes. So don't forget, you can put the function into your calculator. For y2 you can find the derivative. For y3 you put in your answer, and then your task is simply to observe that y2 and y3 produce the same graph and or the same table. If you do that, then you know that you applied your shortcuts correctly. Thanks for watching.